So question 9, we're given that, hold on, where are we? We're given that z is equal to w plus 1 over w, where w is equal to 2 cosine theta plus I sine theta, and we are asked to express the real and imaginary parts of z in terms of theta. So we do what we would normally do, we just substitute in. So z is equal to w plus 1 over w, so it's equal to 2 cosine theta plus I sine theta plus 1 over 2 cosine theta plus I sine theta. Right? But of course, I don't like this fraction because it's got a complex number in the denominator. So I'll multiply by the complex conjugate, which is, of course, cosine, or I don't need the 2 because it's just a constant at the front. So that'll just be cosine theta minus I sine theta over cosine theta minus I sine theta. So I'm just multiplying it to the second term here. So what does that give me? That, of course, leaves me with the 2 cosine theta plus I sine theta plus, and then I'm going to have a half out the front. And then what do I get on the top line? Well, top line is easy enough. I'm going to get cosine theta minus I sine theta. And what do I get on the bottom line? Well, if you look at it, I get cosine squared minus I sine cosine plus I sine cosine, so those two would cancel, and then minus I squared sine squared, so plus sine squared. So I get cosine squared plus sine squared, I just get 1. So this makes our life very easy now. This is just, of course, 2 cosine theta plus a half cosine theta. So this will give me 5 over 2 cosine theta plus I, and then I'll get 2I sine theta minus a half I sine theta. So this will give me 3 over 2 sine theta. So we're asked to hence show that the points representing z on the Argand diagram lie on the curve with the Cartesian equation x squared over 25 plus y squared over 9 is equal to a quarter. So just note, I hope you remember from your graphing techniques that this is an ellipse, which I think is spelled with one L, but never mind. So if I look back up here, what do I see? I see that I have a real part of z, which is equal to 5 over 2 cosine theta. And I've got the imaginary part of z, which is equal to 3 over 2 sine theta. And if you think about it, the real part on the Argand diagram, this is just our x-axis. So I'm just going to let x equal to 5 over 2 cosine theta. And the imaginary part, this is kind of like our y-axis. So I'm going to let y equal to 3 over 2 sine theta. And see what happens. So I'm going to substitute this into my left. So I'm going to say let first. Let x equal to this and y equal to this. Then I'm going to look at the left-hand side of this equation. So the left-hand side is equal to 5 over 2 cosine theta, whole thing squared, over 25, plus 3 over 2 sine theta, whole thing squared, over 9. Well, what's that going to be equal to? So the top line will give me 25 over 4 cosine squared theta over 25 plus, and then this one will give me 9 over 4 sine squared theta over 9. So you can see what's going to happen here. This will cancel, this will cancel, this will cancel, this will cancel. And now I've got a factor of a quarter common. So this is just 1 over 4 cosine squared theta plus sine squared theta. And we know what's cosine theta plus sine theta. That's just 1. So this is just 1 over 4, which is equal to our right-hand side. So we have proven what we were asked to prove. So the next part, show that modulus z minus 2 is equal to 5 over 2 minus 2 cosine theta whole thing squared. Find a similar expression for z plus 2. So what is modulus of z minus 2? Well, this is the modulus of 5 over 2 cosine theta plus I 3 over 2 sine theta minus 2 squared. So what's that going to give us? Well, that's going to give us modulus 5 over 2 cosine theta minus 2 plus I 3 over 2 sine theta. So splitting this up into real and imaginary parts. And then I'm going to take the modulus. So this would be the square root of 5 over 2 cosine theta take 2 squared plus 3 over 2 sine theta squared. Whole thing squared, so I can basically ignore that square root sign. So what does that give me? That gives me, and it's going to take a little bit of time to expand this out, but it gives me 25 over 4 cosine squared theta minus 10 cosine theta plus 4 plus 9 over 4 sine squared theta. So this doesn't look like anything helpful just yet, but what am I going to do? Well, I'm going to use the identity that sine squared here is equal to 1 minus cosine squared theta. Right? So if I do that, what do I get? Something a bit more helpful, I hope. I would get 25 over 4 cosine squared theta minus 10 cosine theta plus 4 plus 9 over 4 minus 9 over 4 cosine squared theta. Making the substitution and expanding it out. Right. And then what do I get? Well, 25 over 4 minus 9 over 4 gives me 16 over 4. That gives me 4 cosine squared theta minus 10 cosine theta. And then 4 plus 9 over 4, that actually gives me 25 over 4. And if you look at this number, what do you see about it? Well, you should be able to hopefully see at this stage that this is 2 cosine theta plus 5 over 2 squared, which is of course, minus 5 over 2 squared, which is of course just 5 over 2 minus 2 cosine theta squared, because the minus sign is within the square, so the plus or minus, it doesn't matter. So this one first or this one first. Either one first is the same. It's the same as multiplying by minus 1 squared, if you will. So I end up with what I was asked to show, QED. What about a similar expression for z plus 2 squared? So again, we go through pretty much the same rigmarole. So this would be modulus 5 over 2 cosine theta plus 2 plus I 3 over 2 sine theta modulus whole thing squared. That would of course end up giving us 25 over 4 cosine squared theta plus 10 cosine theta plus 4 plus 9 over 4 sine squared theta. We make the same substitution. Sine squared theta is 1 minus cosine squared theta, and you end up with 4 cosine squared theta plus 10 cosine theta plus 25 over 4, and that is of course just equal to 5 over 2 plus 2 cosine theta whole thing squared. So that's your similar expression for z plus 2. So the last part of this question asks us to deduce, I believe, that modulus z plus 2 plus modulus z minus 2. Modulus z minus 2 plus modulus z plus 2 is equal to 5. So what is, hold on a second. So we ask ourselves, well, what is modulus z minus 2 plus modulus z plus 2? Well, we know what the square would be, so we know that this is actually the modulus of, rather the square root of 5 over 2 minus 2 cosine theta squared plus the modulus, the square root, sorry, of 5 over 2 plus 2 cosine theta squared. And remember, the square root of the square doesn't give me the answer itself, it gives me the modulus of the answer. So this actually gives me the modulus 5 over 2 minus 2 cosine theta plus modulus 5 over 2 plus 2 cosine theta. So with the square and the square root undoing each other. But if you look at this, 5 over 2 is 2.5. How small can minus 2 cosine theta be? Well, at least it has to be bigger than minus 2. So this whole number here, 5 over 2 minus 2 cosine theta, this has to be at least, so this whole thing must be at least bigger than or equal to 0.5. And similarly, this one also must be bigger than or equal to 0.5 because the smallest that 2 cosine theta can get is minus 2. So I can just get rid of the modulus signs. I actually don't need them here. So let's try and do that very carefully. Oh, not careful enough. Definitely not careful enough. So just get rid of that and put some important stuff back. It's 5 over 2. So we get 5 over 2 minus 2 cosine theta plus 5 over 2 plus 2 cosine theta. These two, of course, cancel out, and you're just left with 5. So we're done.